This lecture will discuss the Doppler effect and interference waves. The Doppler effect is the change in pitch of a sound when the source and observer are moving with respect to each other. Imagine a stationary observer. As the sound source approaches the observer, the sound waves are compressed. The sound the observer hears has a higher frequency because the waves have a smaller wavelength and are closer together. As the sound source leaves or moves away from the observer, the waves are further apart and the frequency sounds lower because the wavelength is longer. When an observer moves towards a stationary source, the wave speed appears to be higher and the frequency appears to be higher as well. The formula for the Doppler effect is shown on the slide, where f prime is the observed frequency, f is the actual frequency, v is 343 meters per second, vs equals the velocity of the source, and vo equals the velocity of the observer. Note, vo and vs are velocities. If the direction is toward, the value is positive, and if the direction is away, the value is negative. Here is a comparison of the Doppler shifts for a moving source and a moving observer. The two are similar for low speeds, but then diverge. If the source moves faster than the speed of sound, a sonic boom is created. The Doppler effect has many practical applications: weather radar, speed radar, medical diagnostics, astronomical measurements. At left, a Doppler radar shows the hook echo characteristic or tornado formation. At right, the medical technician is using a Doppler blood flow meter. A police car traveling at 30 meters per second passes a stationary car. If the police car emits a 500 hertz sound, what apparent frequency do the people in the car hear as it approaches them? The velocity of the source is positive because it's moving towards the observer. Plugging into the equation gives us an apparent frequency of 548 hertz. This is a higher pitch as expected. A police car traveling at 30 meters per second passes a stationary car. If the police car emits a 500 hertz sound, what apparent frequency do the people in the car hear as it passes them? The velocity of the source is negative because it's moving away from the observer. Plugging into the equation gives an apparent frequency of 459 hertz. This is a lower pitch as expected. Waves of small amplitude traveling through the same medium combine or superimpose by simple addition. The two wave functions add together to make a new function. This is called the law of superposition. If two pulses combine to give a larger pulse, this is constructive interference on the left. If they combine to give a smaller pulse, this is a destructive interference on the right. Two-dimensional waves exhibit interference as well. This is an example of an interference pattern. Here is another example of an interference pattern, this one from two sources. If the sources are in phase, points where the distance to the sources differs by equal number of wavelengths will interfere constructively. In between, the interference will be destructive. This is why there is sometimes a dead zone between two radio towers that has very little or very poor reception.